Welcome back, friends. So we were discussing how to use propagator methods to solve the simple process using leading order approximation. We are going to use leading order approximation, and we started with scalar electrodynamics, essentially a scalar particle interacting electromagnetically. Okay, so we started with the Klein-Gordon equation and the Klein-Gordon Lagrangian with interactions, essentially with interactions we call this as scalar electrodynamics or pion electrodynamics. To be more and more specific, I defined the particles involved here to be pi plus and pi minus, and these are a pretty important process. Essentially these are well known process, the electromagnetic corrections to the pion, which are important things which one has to study essentially. Now because we are sticking to leading order, we have these 4 terms in the 3 terms in the interaction terms. The E square term, second order in perturbation theory, I have neglected it because it comes out to be second order in perturbation. So I only kept the first term. The first term, one is the Hermitian conjugate of the other, so there is no, you can consider one of them essentially. So you can consider one of them. So I consider one of them. The Hermitian conjugate means that it is the antiparticle version of the other one essentially. So I consider one of them because, and the example we are considering is pi plus, a simple process. You start with pi plus pi minus going into pi plus pi minus. We will start seeing the diagrams. To write the thing, we solve this entire equations of motion. You derive the equations of motion from here, from the scalar QED, and solve for pi, you solve for phi, and then you try to solve for the scattering processes essentially. So you try to solve the scattering process by solving for phi. Now when you are trying to solve for phi, you realize that there are interactions, you cannot solve it exactly, you have to do it, solve it perturbatively. So you neglect the interaction parts and set it to 0 and solve for phi, for A, and for phi dagger. Phi dagger has the same equation as phi, so it is meaning same solution with which is a Hermitian conjugate of the phi. With this you derive these things, and then from this when you use the Green's functions methods, what for a given process, okay, for a given process say phi going to phi dagger phi going to phi dagger phi, or pi plus pi minus going to pi plus pi minus. You start using the Green's functions method, and the formalism is exactly like what we have seen earlier, essentially in the general form of using Green's functions methods. So the Green's functions methods is similar to time dependent perturbation theory. I am not going to repeat the formalism here. From this formalism you can calculate the change in the wave function in the presence of this interaction term, and how also the Green's function itself changes. So all these things have to be considered. So instead of doing all of that, what we directly did was we can directly write down a bunch of rules essentially. These bunch of rules are given in this particular fashion. So we start with the vertex. The vertex is the one which defines all the interactions. So if you want to calculate the scattering cross sections, you have to worry about the vertex. Okay, so in the vertex you have a 1 pi field and a pi, the current of the pi dagger del mu pi. So phi is actually your wave function essentially, which is nothing but unity with e power I kx essentially will, okay. So with del mu acting on pi and pi dagger. Now if I take a pion field with the pion particle with the p1 wave function, the p1 is picked up by the del mu operating on it, and that gives me p mu, and on the opposite side it picks up on p2, it gives me p2 minus p1. IE is the coupling constant strength. This is what the coupling tells you here, and it multiplies the photon field, which I leave it, I am not putting any wave functions here. This is the coefficient of the product of the wave functions. This is the strength of the coupling which is the coefficient of the product of the wave functions. Okay, this is the coefficient of the product of the wave functions, which is nothing but your coupling constant. That tells you the strength of the interaction. Now you see the strength of the interaction is momentum dependent, essentially it has a momentum dependence in it. So it depends upon what is the initial particle's momentum, and so it can change with momentum, essentially the strength of the interaction can change with momentum. This interaction does not tell you, this vertex, this is called the vertex. The vertex does not tell you whether which one is a propagator. It can be either the scalar or the photon, essentially it does not tell you. If it is a photon, depending upon a process, then you have to treat the photon to be a propagator, whereas if it is a pion, then the pion should be treated as a propagator. The pion propagator is the Klein-Gordon propagator, which we derived yesterday, and the same with the photon propagator is nothing but your electromagnetic propagator, which is I minus eta E mu by q square, and this is nothing but k square minus m square. So what we do, we always define the vertex in terms of a dot or a blob, essentially, in which we have an incoming particle P1 with another outgoing particle with Me2. Now we have to define the external particles, which are free particle. These are your external particles, which are free particles. You have to define these to be what? So we have to define these wave functions. So you write this another bunch of rules for the external particles, and these are your propagators. For the external particles, what we do is that you define according to the charge flow, essentially. So if it is an incoming and charge flow and momentum, essentially if it is incoming to the vertex and the charge is same, that is called as a charge is also incoming, essentially that is called a particle. Charge is moving out, momentum is moving out, it is also called a particle, which has the same way. In this case the wave function is nothing but u, or okay, it is 1. The antiparticle wave function or the coefficient of the wave function is nothing but with opposite charge, it is incoming with an opposite charge. So that is why we define it as opposite arrow with an incoming arrow. For the momentum, this is the momentum P, this is the momentum P, okay. The same thing, it is going out with an opposite charge, it is going out, but with the charge is opposite. It is like treating an incoming particle from the opposite direction with the opposite momenta. It is like treating with an incoming charge particle with an opposite momenta. This we discussed, we were discussing on the Feynman-Stackelberg interpretation and everything, essentially. So this is the wave functions, these are the notation for the particles and antiparticles wave functions, these are the propagators, these are the vertices. Given this set of rules for a given interaction Lagrangian. So for a given interaction Lagrangian, you have this set of rules. Now remember, these propagators are delta function propagators. These are propagators are derived as wave functions for sources of delta function. That is the reason why we have to multiply with the particular strength of the interaction, essentially the particular strength of the interaction. Now with all this, we are now sort of ready to calculate a simple process like pi plus pi minus. Okay, let us start with a even simpler process. So I said we will start with pi plus pi minus going to pi plus pi minus, but we can also start with something simpler. Anyway, okay, let us do this pi plus pi minus going into pi plus pi minus. So what we have is a quantum mechanical interaction in which a pion comes inside, a pi plus comes inside, and a pi minus goes outside, and a pi plus goes outside. This is called a 2 to 2 process. This is called a 2 to 2 process. So, this is called 2 to 2 process. Now, if you give pi P1, P2 for the incoming momenta and P3, P4 to the outgoing momenta, there are 3 ways in which the momentum can be exchanged. Okay? There are 3 ways in which the momentum can be exchanged in this quantum mechanical process, and they form the so called Mandelstam variables. Because this is a quantum mechanical process, you have to see all possible ways the momentum can be exchanged. Say for example, in the first case S, the momentum can be summed over essentially. The momentum can be summed over, the incoming momentum both can be summed over, and that should be equivalent to P3 plus P4 whole square. So, because energy is always conserved, okay, this is the 4 momenta, the energy is always conserved, and so the incoming momenta and the outgoing momenta will always have the same thing essentially. Similarly, you will have T where the difference between the incoming momenta and the outgoing momenta would be exchanged, P2 minus P1 square. Okay. This is also possible in certain process. Given a process which are all allowed, all this whichever is the momentum exchange allowed, that should be exchanged, that should be considered in a given process. So, when you write your scattering process diagrams, you have to be very careful which are all the momentum exchange process which are possible essentially. Now, you can ask the question whether you can have U P3 minus P1 square. So, these are the only 3 possible exchanges possible in a given 2 to 2 process, and they satisfy because remember P1 square is equal to M1 square, P2 square is equal to M2 square, P3 square is equal to M4 square, P4 square is equal to M4 square essentially. Remember that all of them are 4 different mass square. If all the masses, remember for all masses are same, you can show that S plus T plus U is equal to 4m square. In the limit M1 and M2 and M3 are M4 are same, essentially you end up having this 4m square relation. S plus Tu plus U is equal to 4m square. Now, in a given quantum mechanical process, scattering process, you can have 2 particles coming in. It is a relativistic process obviously, okay, and 2 particles going out. In this case, you have to consider any of these things which are all possible. All possible exchanges of momentum are possible. In a given process, sometimes 2 of them are possible, S and T channels could be possible, or T and U could be possible, or something else and something else could be possible. So, all of them have to be considered to calculate the amplitude of the scattering process, to calculate the amplitude. So, one of the 2 main things in calculating the scattering amplitude is something called the matrix element. From here you compute something called the cross section. The cross section contains two parts. One is the amplitude square times something called phase space vector. So phase space factor, which is nothing but mostly a delta power 4, okay, a delta power 4 which is ensures energy momentum conservation. The phase space factor is nothing but P1 plus P2 minus P3 minus P4, essentially it just tells you that the momentum always be 3, and the matrix element is what one has to calculate, which gives you the amplitude. The total cross section sigma, we can do differential cross sections and everything, essentially is given by m square times the phase space factor. Of course, you can now divide it into energy, momenta, and then you get integrals in terms of phase space and phase space integrals and everything. Okay, those are important details which we will which has to be worked out, but those are things which you can learn in your particle physics lectures or some other place, or in which you can pick up on your own essentially also. But what we are more concerned is about calculating this thing that is called the matrix element, essentially, which you can call the matrix element. So what does that tell you? This has all the Lagrangian information. This tells you, these are just kinematics, this is nothing but relativistic kinematics. These are not easy. I am not saying relativistic kinematics is easy or something like that, but it is just, it has to be worked out carefully for each process, the relativistic kinematics, and there is a method. It does not depend upon the interaction, okay. Typically it does not depend upon the interaction, okay. This is something which we can work it out independent of, for any given 2 to 2 process, what is the saying, which is for a given decay, okay, because you can have particle decays in a relativistic system, you can calculate what these are. There is relativistic kinematics, you can compute it and find out. There are wonderful reviews about it, and there are wonderful reviews and there is a particle data group has also wonderful reviews about it, okay. So for the present we will not focus on it, we will mention it when and when required, okay. But what we will show is that what we will be more concerned is computing this matrix element through these Feynman rules which we have seen essentially. So what we have seen right now is that for a given 2 to 2 process, because we are considering this particular process, you can use this Feynman rules, and to use this Feynman rules you have to consider all possible exchanges. This is true independent of whatever technology you are using, if you are using Feynman rules or Green's functions method, they are all equivalent. There is something called the Dijkstrain equation which tells you both the things are equivalent essentially, okay. And now what we are going to do is write all possible exchanges and then compute something called the matrix element for each of these things, and then compute the total cross section about in this particular fashion by multiplying the phase space factor, and the phase space factor is the main thing which takes care of energy momentum conservation, which takes care of the energy momentum. So with this, let us come back to the simplest example we have been considering, which is pi plus pi minus going into pi plus pi minus. So let us write down all possible diagrams with incoming states, vertices, okay. So if a pion is simply moving, you just draw a pion, but it has interactions, right, essentially it has interactions. So pion is an external particle, if there is a particle it is like a pion, okay. Let us not consider the second process, but then it has interactions. So pion has an interaction, it will give out a gamma. This is a virtual gamma, so this can come back here and so on. So, but okay, I will come back to this a bit later. Okay. So, instead of doing that, let us do, because that becomes higher order in calculations essentially, we will come to that. So, let us do a simple process, pi plus going into pi minus going into pi plus going into pi. So, pion comes, which is, let us draw with the vertex a pion, and this is a pi plus. So, this is an incoming thing, and then a pion minus comes. So, this is we had to fix our time direction. So, let us push the time direction to this direction. So, let me call this as P1, this is P2. So, this is moving backward in time, okay. This is moving forward in time. So, this is an antiparticle, okay. This is a pi minus. So, this is a pi plus, this is antiparticle is pi minus, and this gives you a photon, this gives you a photon. In this direction essentially. So, you can have an outgoing pi plus and outgoing pi minus. Okay. I think this should be, sorry, my arrows are wrong. Yeah, now the charge lines are conserved. So, the charges are conserved. Now, you have P1, P2, this has a momentum q, the propagator has a momentum q, this has an external vertex P3, P4. So, the q has a total momentum P1 plus P2. So, q square is equal to p square, and so the first channel you are seeing is called an S channel process. So, for every set of momentum exchange, either S, T or U, we call it as a channel. So, you draw a diagram with all possible channels allowed essentially. So, in this case we had driven the first diagram. Now, we have to see if any other channels are also allowed essentially. We had drawn for the S channel, okay. For the S channel we had drawn it correctly. We have seen that pi plus is incoming, pi minus is also incoming, the momentum direction is this, but the charge is opposite in direction. The momentum direction is this, the charge is in opposite direction. Momentum direction is this, the charge is in opposite direction. The momentum direction is this, the charge is in opposite direction. One thumb rule is that the charge lines always flow like this essentially. The charge lines always flow in a circle. There is no conflict between the charge lines. So, you do not have opposite charge lines coming in. So, you have to be careful, there are different notations, one sets about the momentum, one sets about the charge, some people also use chirality and so on. So, for the present let us look at only the charge lines. So, the first one we have seen is a T channel diagram, okay, S channel diagram. Are there any channels, okay, are there any other more channels? So, this is the second question, are there? Now, can you think of diagrams with external pi's and pi minus such that they exchange a photon and still give you the scattering essentially, whether a pi plus can go, okay, in time and a pi minus can go in time, and without the momentum exchanged, which is in a different type of direction essentially, in a different type of direction. Is that possible? Okay. So, is that possible? Now, will give you a clue, okay. I will give you a clue, or let me try to draw, okay, let me try to draw one particular diagram. So, this is an S channel diagram. So, the answer is yes. So, the answer is yes. So, I have given you a couple of minutes to think about it. So, I hope you can think about it and say there is something called a T channel diagram. So, in which you have pi on, pi plus, pi minus goes it in this direction, pi minus, this is the time direction. It comes in at the vertex, it goes out of the vertex, it comes in the vertex, it goes out of the, but then it exchanges a photon. It exchanges a photon. So, in this particular fashion, essentially it can exchange a photon. This is called a T channel diagram. Why? The momentum exchanged P1, P2, P1, P2, P3, P4 is P1 minus P3, the momentum exchanged, whereas the momentum Q which is exchanged is P1. So, at the every vertex you have to balance the momentum, at every vertex you have to balance the momentum. So, P1 minus P2, Q is equal to P1 minus P2, and P2 plus Q is equal to P4, P2 plus Q is equal to P4, and P1 minus Q is equal to P3, okay. P1 minus Q is equal to 3, okay. So, you know from this you can say P1 minus P2 is equal to Q, this is like a T channel, or P3 minus P1 is also equal to Q, P3 minus P1. This is also correct, essentially this is also correct. Now, this is called a T channel diagram, okay. This is like a T channel, this is one of the three processes which we discussed essentially, okay. And because of the energy momentum conservation, you always have this kind of situations that you have the incoming momenta to be of this P3 minus P1. Now, given this thing, okay, you have T channel, the question then arises, is there any other diagram further, is there a U channel possible? Is there a U channel diagram possible? Now, I will leave you for it, because the U channel would require that pi plus comes down to here and pi minus goes to here. Now, that would violate something essentially. So, think about it, and we will continue from here in the next lecture essentially, okay. I will stop here, okay, I will stop here, and thank you very much all of you.